Imagine trying to learn everything for a massive final exam by sitting down and reading a towering stack of textbooks all at once. You lock yourself in a room, memorize the facts, and try to get smart before you ever step out the door. In artificial intelligence, this is called batch learning. A computer is fed a massive, static pile of historical data, and it studies that information offline, completely separated from the real world, until it understands the patterns. Once that giant study session is over, the training stops. The system is launched into the real world to do its job, applying exactly what it learned without absorbing a single piece of new information. This creates a program that is initially very capable, but totally rigid. It operates under the dangerous assumption that the environment it was trained on will never change. The problem is that the world around us doesn't stand still. Trends shift, technology evolves, and new patterns emerge every single day. When a program's knowledge gets left behind by reality, it suffers from model rut, or data drift. An app trained to identify pictures of cats might stay accurate for years, but a program trained to predict the stock market will start giving bad advice in a matter of days. Updating a batch learning system is a painful process. If the software needs to learn just one new trick, you can't simply add that specific fact to its memory. You have to shut it down, gather the new data, mix it with the old data, and force the computer to reread the entire combined library from scratch. This process requires massive amounts of computing power and hard drive space, and depending on the size of the data, this full reset can take hours or even days to finish. For software that has to survive in a modern, fast-moving environment, relying on these massive periodic study sessions is simply too slow and expensive. So, how do you fix it? You switch to an approach called online learning, also known as incremental learning. Instead of reading a giant textbook once, this system learns like a person reading the daily newspaper to stay up to date. This flowchart shows exactly how an online learning system operates. On the right, you can see new data arriving on the fly. The computer digests this information sequentially in small, continuous chunks, which engineers call mini-batches. Because it only has to process a tiny amount of information at a time, each learning step is incredibly fast. The system constantly adjusts its own internal logic, adapting to new patterns the moment they arrive, while the system is actually out in the wild. This makes it a perfect fit for devices with very limited memory. A Mars rover physically cannot store massive historical databases, but it can hold a small program that learns from what's right in front of it, like the smartphone in your pocket. By taking in data little by little, the software trades the perfection of a giant, exhaustive study session for pure agility. It survives by evolving alongside its environment. That agility also solves a completely different kind of problem. What do you do when you have a massive historical dataset, but it is literally too huge to fit into your computer's main memory? This diagram illustrates a technique called out-of-core learning. You can see at the top left, we start with a mountain of data that is too big to swallow whole. So the system chops that data into manageable, bite-sized pieces. The computer loads just one of those small pieces, learns from it, clears its memory completely to free up space, and then grabs the next piece. It repeats this cycle until the entire mountain is processed. By changing how the machine is fed, engineers take a hard physical hardware limitation and turn it into a completely solvable math problem. When building an online learning program, engineers have to set a crucial dial known as the learning rate. You can think of this as a control knob for the computer's open-mindedness. If you turn the dial high, the system adapts to brand new trends the second it sees them, but as a side effect, it rapidly forgets older information to make room for the new. Imagine using a high learning rate for an email spam filter. It would become so obsessed with catching today's newest spam tricks that it would forget the classic scams from last month, letting them slip right into your inbox. If you turn the dial low, the system learns slowly and stubbornly. It won't adapt immediately, but it won't be easily tricked or thrown off course by weird random data spikes, which engineers call outliers. Finding the perfect learning rate requires balancing two opposing forces, deciding how quickly you want to embrace the future without erasing the valuable lessons of the past. Because online learning programs adjust their internal logic on the fly, feeding them garbage data will immediately tank their performance. Sometimes this happens purely by accident. A malfunctioning temperature sensor on an industrial robot might start sending wild, static-filled readings. If the robot tries to learn from that static, its behavior will break down. Other times, it is completely intentional. Malicious users might flood a search engine with artificial clicks, feeding the system bad data to trick the algorithm into boosting a specific web page to the top of the results. A live system is constantly exposed to the chaos of the real world, and when it learns a bad habit, its mistakes are instantly visible to the people using it. To protect these systems, human engineers must constantly monitor the live output, watching for sudden drops in quality. If the system starts acting erratically, the team has to engage a virtual kill switch. They turn off the learning function entirely and revert the program's brain back to yesterday's stable state. As a proactive shield, engineers often build an anomaly detection algorithm. It acts like a bouncer at the door, scanning incoming information and filtering out weird, abnormal data before the main system can ever learn from it. Whether a computer gets its intelligence from the deep, static study sessions of batch learning or the fast, reactive street smarts of online learning, these machines cannot operate alone. They rely on human-designed boundaries to safely make sense of a chaotic world.